Hi there. Today we are beginning Chapter 5. Chapter 5 is all about electrons in atoms. And some of the basic concepts of where the electrons are in atoms you did learn in middle school, but we're going to go into a much greater depth with the ideas of quantum mechanics and orbitals on top of energy levels. And the first way that we sort of begin by talking about electrons and atoms is by talking about this phenomenon called atomic emission spectra. Basically, this is what scientists observed in the early 1900s, late 1800s, that started to get scientists to think a little bit more in depth about what was going on with light and energy and electrons. And so you can see on the picture on the left, you see that there's just a typical light bulb. And the typical light bulb, when it is illuminated, kind of glows like with a white light. And when we put that through a prism, we see the entire rainbow of colors, Roy G. Biv. But if I take hydrogen gas, and only hydrogen gas, and put electricity through it, which is what the picture on the right is showing. Sorry, the picture on the right is actually showing helium. Works for helium or any other element. When I put electricity through helium, I don't see the entire rainbow. I just see these very specific lines of light, very specific colors, and colors are analogous to energies. So the question was, where is this energy coming from? Why is it that only certain amounts of energy are coming out of a helium atom? And the only way that scientists could explain that is if they thought it had something to do with the electrons. So eventually we're going to tie atomic emission spectra to the concept of where the electrons are in the nucleus, just so that we all start with the same general definition. What is an atomic emission spectra? It's that when I say that word, I'm referring to this picture. And the idea is when electricity is sent through a gas, colored light is released, and when that colored light is sent through a prism, we see specific lines of color. So we're going to need to start talking about what exactly is light to understand how this picture on the right helped us to understand where electrons are in atoms. Light is kind of the general term for something that we call electromagnetic radiation. Electromagnetic radiation is energy in the form of a wave. And so this energy in the form of a wave has characteristics that all waves have, specifically wavelength and frequency. Wavelength is symbolized by the Greek letter lambda. It kind of looks like an upside down Y. So wavelength is symbolized by lambda, and it is literally the distance between two peaks on a wave. So the distance between, right here, one peak and another peak. And then frequency is how many times a wave passes a specific point in 1 second. Very similar to the way that we use frequency when we are talking in everyday life. We may say that, how frequently do you go to the dentist? And you would say, twice per year. It's number of times per a unit of time. Specifically for electromagnetic radiation, we mean how many times does a point pass by in 1 second. If we think about this wave moving, and here's a little guy there. If this wave is moving, we can see that depending on how big the wave is, what speed the wave is traveling, that a number of points would pass by my little guy in 1 unit of time, seconds. So frequency is the number of waves that pass a point in 1 second. The unit for wavelength has to be a length. So it is often in meters. Sometimes it can be in nanometers, but it has to be a length. The unit of frequency is a number per unit of time. So it is often the unit is 1/seconds, kind of strange, or you might have heard this one before, hertz. And how are those related? How are wavelength and frequency related? Well, looking at this picture, you can see if I have a low frequency, that corresponds to a long wavelength. If this is the little guy right here, right, and this wave is traveling, because there is such a long wavelength, we would see that the number of waves that pass by a certain point would be fairly small. As opposed to in the diagram on the right, there's my little guy again. If you are moving, if the wave, I should say, not you, if the wave is moving towards the right, now that the wavelength is shorter, there's going to be a greater number of waves passing per second, so the frequency would be higher. This can be mathematically represented by the formula speed of light equals wavelength times frequency. And this speed of light is a constant. It's always the same number, 2.998 times 10 to the positive 8 meters per second. That is a number that when you're in class, I'll show you how to store that on your calculator so you don't have to type that number in every single time. And so the speed of light is in meters per second, and that's equal to wavelength times frequency. So let's do a few practice problems with this. So the first one, I'm giving you the wavelength of 4.30 times 10 to the positive 10 meters. And I want you to convert that to frequency. Remember, in every single problem that we do, we write the formula, we show the numbers that are plugged in, and we write the answer. So what is the formula? Speed of light equals wavelength times frequency. Now I plug in the numbers. Right? I'm using the symbol for frequency, which is the Greek letter nu. It kind of looks like a scripty V or a cornucopia. I don't know. It is what it is. Try your best to make that symbol. So now I've plugged in all my numbers, and now I solve using algebra, dividing both sides by 4.30 times 10 to the positive 10. Okay, so on the right-hand side, those two numbers cancel out. On the left-hand side, the meters cancel out. There's a meter in the numerator and a meter in the denominator. Therefore, my answer will be that my frequency is equal to 0.006972. And now I have to choose, how am I going to round this with significant figures? The speed of light has 4. The wavelength in the problem has 3, so I'm going to round my answer to 3 significant figures. So this is equal to 0.00697, and the units are going to be 1/seconds. Remember, beginning zeros are not significant, so just the 6, the 9, and the 7 are significant, and I have my units in there. I have 2 more of these problems. If you think you've got it, you can pause the recording now, do the problems, and then check your answer, or you can just keep following along with me. The next question, I give you the frequency, 3.73 times 10 to the positive 9 hertz. Hertz are another way of saying 1/seconds. So I write the formula, speed of light equals wavelength times frequency, plug in the numbers that I know, 2.998 times 10 to the positive 8 meters per second. I'm going to solve for the wavelength. The frequency is 3.73 times 10 to the positive 9. And I usually go back to 1 over second so I can see how the units cancel out. Divide both sides by 3.73 times 10 to the positive 9. Look at how my units cancel out. Everything on the right cancels. My seconds in the denominator cancels. The speed of light has 4 significant figures. The frequency has 3 significant figures. So my answer will be 3 significant figures, 0.0, I think I said my wavelength will be 3 significant figures, 0.0804 meters. And that's my wavelength right there. Beginning zeros, not significant. And then the last practice problem is a little bit trickier because this time my wavelength is in nanometers. In order for my units to cancel out, they have to be the same on both sides. So the first thing that I'm going to need to do is to take my 575 nanometers and convert it to meters. 1 meter on the top, 10 to the 9th nanometers on the bottom. Those units cancel out. I get 5.75 times 10 to the negative 7 meters. Now I use my formula. Speed of light equals wavelength times frequency. The speed of light is 2.998 times 10 to the positive 8 meters per second. My wavelength is 5.75 times 10 to the negative 7 meters, and I'm solving for nu, for my frequency. Divide both sides by 5.75 times 10 to the negative 7 meters. Everything cancels out on the right except for the symbol for frequency, nu. Meters cancels out. 2.998 has 4 significant figures. 5.75 has 3. So my answer turns out to be, with 3 significant figures, 5.21 times 10 to the positive 14, 1 over seconds, equals my frequency.